Welcome back to another episode in Practical Electronics and Circuits 101. In this series, I explain the fundamentals of circuits with a focus on using this knowledge for practical applications and projects. The link to the full playlist is in the video description in case you want to get caught up with previous videos. In the last several videos, I covered passive components such as resistors, capacitors, inductors, and transformers, which means that active components are up next. But before we get into those, I think now would be a good time to do an introduction to circuit analysis and Kirchhoff's circuit laws. Now, to be honest, the usefulness of circuit analysis will depend on what you're trying to do. If your goal is to get into engineering and design, then circuit analysis is definitely something you need to learn. Likewise, if your goal is to debug and repair broken equipment, then circuit analysis is also a requirement. But if you're mainly interested in building some projects and simply following existing schematics, then circuit analysis isn't all that important. It depends. It's still good to understand it, but you certainly don't need to be an expert in it. Since the main focus of this series is to get started on some projects, I won't be spending that much time on circuit analysis. But like I said, it's still good to understand what it is and how to do it. So today let's go over what it is and do a few quick examples which should be sufficient to gain a good understanding of it. Now when we say circuit analysis, what we're actually talking about is Kirchhoff's circuit laws, which is composed of two laws. The first is Kirchhoff's current law, or KCL for short, and the other is Kirchhoff's voltage law, or KVL for short. These laws are named after Gustav Kirchhoff, who was a German physicist from the 19th century. Kirchhoff's laws regarding circuits are extremely fundamental when it comes to solving problems and designing circuits. In a nutshell, KCL states that the algebraic sum of currents in a network of conductors meeting at a point is zero. So if we look at the current flowing through this point that's labeled A, this means that the sum of the two currents leaving this point must equal the current that's flowing into it. Now, if we looked at a different point that's being split into three paths instead of two, then the sum of these three currents leaving the point must equal the current that's entering it. Now, KVL, on the other hand, states that the directed sum of the voltages around any closed loop is always zero. So if we looked at this circuit here, we have a voltage source power supply and a few resistors. The voltage source is considered a positive voltage, while each resistor creates a voltage drop, which is considered a negative voltage. KVL states that the sum of all these voltages must equal zero. So now let's work through a few examples using these laws. Let's first start with KCL. We have this simple circuit here, and we want to find out the total current being used. At the junction B, we have two currents exiting, I1 and I2. According to KCL, if we calculate these two currents, then we can solve for the total current of the circuit, which is labeled IT. We can use Ohm's law to calculate I1 and I2 since we know the two resistor values and we know the supply voltage is 24 volts. I1 equals 24 volts divided by 8 ohms, which equals 3 amps. I2 equals 24 volts divided by 12 ohms, which equals 2 amps. So now we can use KCL and simply add I1 and I2 together to get the total current of the circuit, which is 5 amps. Since this was an extremely simple example, let's do one more slightly harder example for KCL. Again, we have two resistors in parallel, but now we also have a third resistor that's in series with those two parallel resistors. There are a number of ways to solve this problem, but let's do what's called the loop method, where we draw a complete loop around each path of the circuit. So this would be the first loop, and this would be the second loop. Now we can use Ohm's law to represent each of these loops and associated currents for each path. Again, we have three different currents to solve for. I1 is the total current and it's equal to I2 plus I3, as we already know from KCL. We can use this fact along with algebraic substitution in order to solve for the current values. So let's first replace I1 in both equations with I2 plus I3. Now we can expand the equations and combine like terms, which leaves us with these two equations. We still have two unknown variables though, so in order to solve this we need to get rid of one. We can do this by multiplying the first equation by 4, then subtracting the second equation from the first, and after working this out, we end up finding that I2 equals 1 amp. Now in order to solve for I3, all we need to do is plug I2 into one of our previous equations and we find that I3 equals half an amp. Now the only thing left is I1, which is the total current. And as we know from Kirchhoff's law, the total current for this example is I2 plus I3, which comes out to 1.5 amps. So as you can see, simple examples like this are really just an exercise in algebra using Ohm's law. Now let's move on to a quick KVL example. Let's say we have this circuit here with a 12 volt power source and 3 resistors whose values are 10 ohms, 20 ohms, and 30 ohms. And we're asked to find the voltage drop across each of the resistors. In order to solve for this, the first thing we need to do is calculate the current going through the circuit. We know the total resistance is simply R1 plus R2 plus R3, which comes out to 60 ohms. Now we can use Ohm's law to solve for the current. This comes out to 200 milliamps. Now we can use KVL to solve for the individual voltage drops across each resistor. KVL states that the voltage from the power source plus all the voltage drops across the resistors must equal 0. So if we substitute each of these voltage drops with Ohm's law, we end up with this equation. Now if we solve for each voltage drop, we'll find that V1 equals negative 2 volts, V2 equals negative 4 volts, and V3 equals negative 6 volts. We know these values are correct since the equation comes out to 0, just like KVL says it should. Now there is a few more things I wanted to say about KCL and KVL before wrapping up today's video. The first is that what I showed today is only an introduction, so if you want to become proficient at solving these, you should definitely do more problems on your own. But like I said at the beginning, it's usually not necessary to do these problems if you're only interested in building existing designs and following schematics. Unless you run into problems and need to pinpoint where the issue is, in which case you'll likely need to work out some equations. If you want to be able to debug and fix broken equipment, then you should definitely spend more time practicing these problems. When fixing broken equipment, the first thing you'll want to do is inspect the board for any components that are visibly damaged and replace them. But sometimes busted components won't always show physical signs of being damaged, which makes things more difficult. There's a few other things you can do to debug the circuit before moving on, but usually, this is where you'll want to start measuring voltages around the circuit to determine where the issue is. But how do you know what the voltages are supposed to be? Well, you'll need to get a schematic for the circuit you're looking at and work out the KCL and KVL equations for it. Then compare these values to the values you measured. If the voltages you measured in a particular spot are drastically different from the calculated values, then you know the issue is in that location. If you're dealing with active components and ICs, then you'll also want to look at their datasheets to determine what sort of voltages you can expect from those components. So if this is something you'd like to get better at, then here's a homework assignment for you. I suggest watching more YouTube videos on KCL and KVL that go through more advanced problems. There's plenty of videos out there that do this. I'd say watch a total of at least 10 or 20 different problems and make sure you understand how they did each step. Then afterwards, write down each problem on a physical piece of paper and solve each of them on your own. If you're able to do this, then I'd say you should have a pretty good understanding of these concepts. But like I said before, if you're only interested in building projects and following existing schematics, then it's not really necessary to do this. As long as you understood the examples I did today, then you should be okay. Now the last thing I wanted to mention doesn't just apply to KCL and KVL, but math equations in general. Keep in mind that most mathematical equations are describing an ideal situation using ideal components. In reality, nothing is ideal or perfect, so don't be surprised if your calculated results are slightly off compared to the actual values that you measure with a multimeter. There's a few reasons for this. For example, real resistors are almost never exactly the values that's printed on them, and there will always be some variance between them depending on their tolerance value. And small variations like this can sometimes make an impact on your results. The same concept applies to capacitors, inductors, transistors, and every other component. In addition to this, copper wires and traces in a circuit board also aren't perfect. And not only do they contain a small resistance, but they also contain some level of capacitance and inductance as well. In certain applications, this can be a big problem. For example, when dealing with high-frequency signals, let's say in the gigahertz range, special attention needs to be taken when designing a PCB and its traces in order to minimize stray capacitance, inductance, and other undesirable qualities. If you were to attempt to build this on a breadboard, then you'll likely have a ton of problems, since breadboards aren't meant to handle such high frequencies. Most of the projects I plan to do on the channel will work fine on a breadboard and can tolerate the small variations I just described. But in general, you should always keep in mind that there's a lot of variables at play, and it's difficult to account for all these imperfections when doing equations. So it's perfectly normal for your measured results to be slightly different from your calculated results unless you spend the time to factor all these things into your equations. But most of the time, this level of accuracy is not necessary. Alright, well that wraps up today's lesson. If you have any questions, then feel free to ask in the comments section. And if you learned something today, then be sure to give the video a thumbs up. Also, subscribe to the channel if you haven't already, and hit the bell so you can stay up to date on new videos. As always, thanks for watching, and I'll see you in the next one.